definitely. I'm Arash, and I'm presenting CBMPC on behalf of the applied cryptography team at Coinbase, including myself, Yisho Chen, Yehuda Lindell, Gil Segev, Valerie Asheter, and Samuel Ranalucci. So this is a talk that I gave about a month ago at Science of Blockchain, hence the date of August 5. I didn't make a typo, just wanted to call that out. I know today is September 5, so, and as opposed to that talk, this is not going to be a monologue. So I will of course, do the presentation, but at any time, if you have a question, feel free to interrupt me and ask. And since I have the Zoom meeting on another screen, if you type a message, I may miss it. So if you have a question, please unmute yourself and ask. All right, with that being said, let's start the presentation. So I'm assuming that most of you are familiar with MPC, but in case you're not, by MPC, I mean Secure Multi-Party Computation, which is essentially a cryptographic tool that enables multiple distrusting parties to perform a computation over their joint private inputs. Okay, so they don't trust each other, they don't trust anyone else, they have private inputs, and they want to perform a computation on those private inputs. And this is very ideal for managing keys in a cryptocurrency scenario because, by the way, I have a cold, hence this coughing and noise, my sound, apologies for that. So you can think of the application that we want to do is a digital signature, right? That's the function that we want to perform. And the private inputs are essentially going to be private shares of the signing key. So multiple parties each have a private share of the signing key, and they jointly want to perform the digital signature. The reason that this is a very good match for the crypto key management is that it removes a single point of failure. Meaning that if in the past an attacker would have to just compromise a single wallet or a single location and steal the key and then steal the funds, and now the attacker needs to go and compromise multiple different machines. And if the designer of the system is careful, they would put those machines into different environments, one in a cloud, one in a mobile, one in a, for example, laptop, and even in the cloud, maybe one in Amazon, the other one in Azure. So different environment, different access control, and all of this makes it much, much harder for an attacker to go and compromise all the different places to steal the full key. Okay? Now, as you may have been following the news, and you may know that to steal the funds of a wallet, you don't necessarily need to steal the key. If you can compromise the system that is setting the address and the amount, you can again drain the wallet, because the signer will sign thinking that it is that they are sending some Bitcoin to a certain trusted address, but in reality they are sending it somewhere else. With this distribution of parties, we can have distributed access control as well. So each system will have its own way of making sure that the transaction they are signing is correct. Again, for an attacker to compromise all of that is going to be very hard. So that's why this is a good use case for MPC. And we have been using it with great success inside Coinbase for our custody and consumer wallets. And we have decided to open source this to in essence, to raise the security of everyone. Because much like us, the community has recognized the MPC to be a good solution. However, it's very hard to come by cryptographic expertise needed to create these cryptographic systems. And some of the libraries that are out there may not be up to the standards that we bound ourselves to. And we recognize that any breach to any organization is going to be bad for industry and by extension bad for Coinbase. So our hope with releasing this open source library is to make sure to raise the standard, the security standard of the field. Moreover, by open sourcing, our customers will get a chance to look at how we write code, what is our process, and how we protect their funds, and of course, gain their trust. Uh, we also get to benefit by having the community look at our code and finding bugs. And this is something that I think Lee is very interested in. And I will talk more about what are the places that there might be bugs, and I would love for you guys to take a look, take a deeper look. And I will talk about our bug bounty program at the very end of the presentation. All right. So our code, you can find it in under GitHub Coinbase/CBMPC, and then I will, if we have time at the end, I will share my screen and walk over the code as well. But for now, we have essentially split our functionalities into 3 different parts. The crypto is short for basic cryptographic. This has things like TDH2 threshold encryption. So this is a threshold decryption system. So it's not signing, it's a threshold decryption system. We have things like modular arithmetic, various elliptic curve operation, Paillet and Elgamal homomorphic operations, commitment, secret sharing, Lagrange, and different ways of generating random values. On the zero knowledge side of things, we have Fiat, Shamir, and Fishlin. We have various proofs for elliptic curves, including decisional, including Diffie-Hellman and discrete log. We have proofs on Paillet keys and Elgamal commitments, and we have range proofs. Then on the protocol side, where parties have a line of communication with each other and then run a multi-round protocol, we have different ways of generating random values for coin tossing, using coin tossing. We have a committed group broadcast and pairwise broadcast, integer commitment, OT and OT extension, publicly verifiable encryption, DKG, both for two-party and multi-party. We have a way of deriving we have a way of deriving keys that are compatible with HD wallets. This doesn't use the standard hashes under the hood. It's rather it's an MPC friendly way of doing that. And we have EDDSA and ECDSA, both 2PC and MPC protocols to generate the signature. All right, so by this point, you might be wondering, all right, there's a library, Coinbase is releasing it. Why should I care? What's difference between this library and maybe other libraries? And to try to convince you to give us a try, I'm going to dedicate the rest of this presentation to talking about our guiding principles, including our conservative security posture, our production grade code, and our rigorous and transparent process of research to code. So let's start with the first one, the conservative security posture. So for our security model, we use simulation-based universally composable security, or for short, UC security. Which means that we won't even try to rely on game-based definitions, and all our protocols are secure against malicious adversaries. For our proof model, we assume random oracle model. So meaning that we use random oracle model, but even there we use it in a very limited cases. For example, in commitments or when using Fiat Shamir, so to make the protocol non-interactive. We do not use any generic group model. As for assumptions, we use the 90s era of assumptions. And I put this 90s specifically because the definition of a standard assumption is different based on who you ask. And but We rather rely on the 90s era because they have stood the test of time. And these are what we are more comfortable relying on when we are protecting billions of dollars. These, for example, include decisional Diffie-Hellman or pi-m, and not, for example, the more recent assumptions. Nothing against the recent assumptions. They may turn out to be good assumptions, but they haven't proven themselves because they are assumptions and they haven't proven themselves long enough in the field. We'd rather not rely on them. And this conservative approach of security over efficiency is something that I want to emphasize on by talking about an example. So consider the universal composable security for the non-interactive zero-knowledge proof of knowledge. So for those who are not familiar, the zero-knowledge proof of knowledge means that you have a secret value. You want to prove that you know it. So it is a proof of knowledge. And you want it to be zero knowledge. So in the process of proving, you don't want to reveal anything about that secret value. And it is non-interactive. So you want to have just you create the proof in one statement and rather than interacting with the verifier. And there are two ways of doing this. One is the Fiat-Shamir heuristic, which relies on the forking lemma, and the other one is Fishlin, which is a straight line extractor. Now, in the UC security world, we get soundness by using Fiat-Shamir, meaning that a dishonest prover cannot prove a false statement. We get zero knowledge as well, but we do not get proof of knowledge. Then this is because of the forking lemma. So, meaning that so the forking lemma, again, for those who are not familiar, the forking lemma works on a Sigma protocol where you have a first message, right? You record that first message, you continue the protocol, get the second message and third message, and then you rewind back to the beginning of the second message, and then run the protocol again and get the different second message and different third message. Now you have the same first message and two different second and third messages. You put them in an equation, solve a linear equation, and then extract the secret. And that's how the proof of knowledge works. But that will fail in the UC world because in the universal composable model, you are not allowed to rewind. Okay, and so with Fiat-Shamir, you don't get UC security, but you get soundness and zero knowledge. With Fishlin, on the other hand, you get all three, and you're still within the UC security model. So, looking at this, you might be wondering, all right, Fishlin is clearly better. Let's always use Fishlin. Why doesn't everyone do that? And it's because of the efficiency. So Fishlin is much slower than Fiat-Shamir. In naively looking at the paper itself, I think it is 2 or 3 orders of magnitude slower than the Fiat-Shamir, and that's what has made people not even approach it. And as far as I know, none of the libraries out there use Fishlin. However, we said that we want to be UC security. Let's put some effort in it and see what can we do. And before talking about our results, I want to motivate the example and and describe 2 zero-knowledge protocols, and then I'll talk about the results and say what we have achieved. So let's talk about the Diffie-Hellman, zero-knowledge Diffie-Hellman. So assume that we have an elliptic curve over a appropriately defined group, and the G, H, A, and B are 4 elliptic curve points in that group. And we have a secret W, and we want to prove that A is W.G and B is W.H. And notice that this statement on its own is very interesting. So there is something to prove. The soundness is meaningful here, meaning that we do want to prove a W exists, that this relation holds. Okay, so the soundness is interesting. The proof of knowledge may be interesting, maybe not. So whether I know what that W is or not is application dependent. Okay. And in all our protocols in CVMPC, we don't really need to prove that we know W. Just the fact that the W exists is enough for our protocols. Okay. Therefore, for zkDH, we do use fiat shamir, and we are still within the UC security bounds, and we get to enjoy the efficiency gains of the zkDH. On the other hand, when we go to the discrete log, the zero knowledge discrete log, we have a G and A, and we want to prove that A is W.G. So there is a secret W such that A is WG. And well, let's say G is the generator of the group. Now, here, soundness is trivial. All the points in the curve will have such a W. So proving that the W exists is not interesting at all. And we don't care about it, essentially. What we do care about is whether the prover knows W. So the proof of knowledge is really important here. So in this case, we do use Fishlin. Okay, so now let's see some numbers.
Sorry.
If you go to our benchmark page, and you can see the list of all our primitives and how they measure in at least GitHub servers. zkDH is 0.08 milliseconds, and zkDL is essentially one millisecond. And this is after heavy optimization, meaning that after heavy optimization, Fishlin is 15 times slower than fiat shamir. And so from 2 orders of magnitude to 15 is a huge improvement, but it is still 15 times. And people might look at that number 15 and say, wow, this is too slow. But what I want to point out here is that, yes, it is 15 times more slower, but it's just a millisecond. It's not really that big of a deal, especially when you are using just one of these in a signing protocol, and that signature is going to protect billions of dollars. So if someone abused that the signing protocol, it could result in a loss of $1 billion. So, and this is in the context that a typical transaction in blockchain takes between 10 seconds to 10 minutes, right? So if you're protecting that amount of money and your typical transaction time is in the order of seconds and minutes, then saving 1 millisecond isn't really worth it. And it's best to rely on conservative security assumptions and work within the UC security and then enjoy all the guarantees that come with it.
Sorry, Arash.
Yes.
Well, do you want to go, Aravind?
Yeah, so just a quick question, Arash. Probably I missed that. Why is the Fishlin one preferred over fiat shamir? Is it because of the soundness?
It's because of the proof. For the proof of knowledge to be, let me go back here. So we prefer Fishlin in the UC security world because we can have proof of knowledge.
Right. Okay.
If you don't care about UC security and you are in a standalone model, for example, or you are in a sequential model and you don't care about concurrency, then you can gain proof of knowledge with fiat shamir as well.
I see. So that's what you mean by conservative. The model being UC is what you mean by conservative security.
Yeah, we don't, meaning that in some one way of looking at it is that you want to design the most optimized solution, right? And then you would use Fishlin and say, it's fine. I'll take the chance and say that let's assume that I'm running in a vacuum, nothing else is running beside me, and I'm the only thing in the world. If this protocol is the only thing in the world that's running, right? So that's not a very conservative view of the world. But if you assume UC, you are assuming that you have a malicious environment, everything is running in parallel. And in that scenario, you no longer can get proof of knowledge with the fiat shamir.
So you're saying this 1 millisecond when you compare it to the scale of like transaction acceptance times, we can tolerate that.
Mm-hmm.
Will it become? I mean, have you tested or have you checked cases where this could actually become a bottleneck?
We have not tested it, at least in our protocols, the ones that we care about and we have released, it has not shown itself.
Okay.
But of course, I mean, if you are running this signing transaction 1 million times per second, maybe it's it becomes important. But even at our scale, it's not a problem.
Okay.
And yeah, my question was just on the slide before.
Or more.
Yeah, I think just was it the slide before. Yeah, yes, the Diffie-Hellman. Could you just go over again why the Diffie-Hellman doesn't need the was it the proof of knowledge? Oh, Fiat-Shamir gives.
Sorry, no. In the Diffie-Hellman, both the soundness and proof of knowledge, both of them are interesting, meaning that you can prove maybe there is a W1 here and a W2 here, and these Ws are different, right? Or maybe they are the same. So proving that the same W is used is the soundness, and this is important on its own. Proving whether you know that W is also important. That's separate, right? Both of these are important. In our protocols, proving that you know W isn't important. So in our use case, proof of knowledge for ZKDH is not important. Maybe in another use case, in another protocol, it becomes important.
Okay, so is it that you use the Diffie-Hellman and the discrete log just differently in your protocols, and that's why there's the difference?
In the discrete log, soundness is never important because there is always a W that this relation exists. So you don't even need to prove it. It's trivial. So the only property that you care about is whether you know W or not.
Yeah.
So with discrete log, there is no choice but to use Fishlin if you want UC security. With Diffie-Hellman, depending on your application, you either use Fishlin and get UC security or use Fiat-Shamir and still get UC, depending on the application.
Okay, thank you.
Cool. All right. So now let's talk about our parameters. So we use 64-bit statistical security as our default, but in some cases, when the efficiency gain is significant, we reduce it to 50. This is for some of our interactive cut and choose ZK protocols. And we noticed that because it is a statistical parameter and you essentially have one chance to get it right, this 14-bit reduction in security is still tolerable. It is still okay. We are okay with that, even when protecting billions of dollars. As for the computational security parameter, we use 128 bit, which is in line with 256 bit of elliptic curves. And we do not use any shortcuts to reduce this computational security parameter. So, for example, we don't use 80-bit for ZK proofs. Now, this is both important in terms of our mindset in this library and also what you can get out of it as the user. So we try to have secure defaults. What does that mean? So when you're dealing, for example, with Pi8 ciphertext, any homomorphic operation you do, the result will potentially leak something about the secret. So before sending the result to your counterparty, you need to re-randomize it. So, and we do that by default. So anytime we do a homomorphic operation, we re-randomize it. But this becomes very inefficient if you are doing a chain of homomorphic operations and then you want to send the result. That's why we made this overridable. So for example, in our ECDSA 2PC protocol, we do a chain of them without re-randomization, and then at the very end, we re-randomize and then send the result. So this approach of using secure default, but letting the user decide when to override them is one of the things that we have tried to incorporate in our design. Similarly, when it comes to session IDs, all of our protocols generate a unique session ID internally if you don't pass anything. Sometimes it's just interleaved within the rounds of the protocol and it doesn't add any round. Sometimes it just add one extra round to make sure that we create it. But if the user chooses to pass in an SID as input, we'll use that. We trust the user and we use that. So same type of behavior. All right. Another part is that we have tried to make the code constant time. And what this means is that whenever we are working on a secret, we want to make sure that the computation, the time it takes to do a computation over that secret is independent of the value of the secret. That's what we mean by the constant time. This is CPU architecture dependent, and we have documented how we have achieved this in our constant time PDF under the docs. I won't go into details now, but I encourage you to take a look at it. All right. So,
Arash,
yes.
a quick question. So, a few slides back, you had shown this table of algorithms, protocols that you did, right? So, my question is regarding the proofs. Are you also doing like batched versions of those statements, or are you just doing like a single one-shot proof?
Depends on the use case. Sometimes we have batch, sometimes it's just a single.
So
So for
is like
example,
can your library like handle these batched one? Like, do
yes,
you also have batched optimizations available?
yes,
Okay,
yes,
okay,
but
okay,
not for everything. For example, for ZKDL and ZKDH, both of these have a batch version.
okay, okay.
But for example, the ZK Elgamals, I don't think we have a batch version of it. So
Okay.
essentially, we have tailored it to our need. If we saw a bottleneck, we make sure to optimize it and create a batch version.
Okay, perfect. Thanks.
All right. So now on our second guiding
Sorry,
principle.
Arash, one more question. So, what was like for some of these proofs, what's the choice of like the group that you used? Like, what was like the driving factor? Like, do you care about compatibility with like existing implementations, or like you just went for something that was the fastest, or can you comment on
Right.
that?
So we sometimes the choice is made for us. So for example, we are working with we are generating an ECDSA signature. So our group is the SEC256, right? Sometimes when we are doing OT, the choice is ours. We can
Okay.
do the OT either on SEC256 or P256, and in that case, we default to P256 because that's faster. So when we have the choice, we choose the one that gives us the same security but more efficiency.
Okay, so essentially, there's like a choice of curve is also something that
Yes.
The user can
Yes.
put in. Okay, perfect.
Yes. Even if I'm not mistaken, even with ECDSA, you can pass a different curve. With ECDSA algorithm, you can pass different curve. Same for Schnorr.
Okay, perfect. Thanks.
All right. So, production grade. Apologies. Right. So our code is heavily tested, documented, and audited. We have this process of we do release incremental changes, but we don't mark it as, for example, final or released or tag it before it is audited. And we make sure to heavily test both the running, for example, the constant time test, fuzzing it internally, and various unit tests. Our code is written in C++. We have Go wrappers on top of it. And we are hoping to add more wrappers for other languages over time to make it easier to include in whatever language that you choose to write your software in. As has been maybe apparent in our discussion and questions so far, we are focused on the cryptocurrency use case. So we are not trying to be a general MPC library. So for example, you won't find things like a garble circuit in there, but it's not just threshold signing. We have, for example, things that are useful in the cryptocurrency use case. For example, publicly verifiable encryption, where you can encrypt something, a secret value, and that has a corresponding public value, and then you can prove that what you have encrypted is correct without decrypting anything. So it's publicly verifiable. And we have threshold decryptions, threshold encryption system. So anyone can encrypt like any other encryption system, but a threshold of people are needed to perform the decryption, and many other similar things. Right. So we have. I just want to emphasize that this focus on conservative security doesn't mean that the library is going to be slow. Quite the contrary. We have made a lot of effort to make the library very fast. For example, if we get a bunch of benchmarks, compare a bunch of benchmarks from the original Lindell 17 paper and ours, you will see that in the keygen and signing, we have made quite a lot of improvement. However,
were they
yes.
both using like the same language, or is it different languages?
Same language, but not same hardware. So some of this is probably because we are running on better hardware. I didn't have access to the original code, so I couldn't run a side-by-side test. Yeah, but the gains are big enough to mask some of the hardware.
Yeah. And is there any use of pairings?
No, not in our library so far.
Is that because of the security, or is it just because of efficiency, or just not using the constructions?
We haven't. I think pairing is used in BLS, if I'm not mistaken. That's the only use case that I can think of. Maybe I'm mistaken, but that's not something that we are supporting right now. Yeah. All right. So on the signing, this is the I talked a lot about UC security. Signing on ECDSA2PC is the only place that we break that rule, but we also provide a full UC simulation-based signing as well, and I'll talk more about it. So the original signing protocol required something, but was designed with something called global abort, meaning that if the signing fails, a single bit is leaked about the private key, and therefore no other signing protocol that was running concurrently to this should continue. So you need to go and stop everything else that is running concurrent, and you shouldn't run any further protocol. So that's why it's called a global abort. And this if you design your system right and be careful about this, you get quite a efficient signing protocol. And the proof of this is a game-based one. We kept it in the library because of its efficiency, but it is not the default, and it is clearly marked that it is signed on. So you will call it only if you really want to. The default signing that we have used is a UC secure one. It is a bit slower, not the end of the world. It's quite performant actually compared to the rest of the system. But yeah, you get the full UC secure signing out of the box by default. And if you know what you're doing and you care about that 50-ish millisecond, then you can use the signing with global abort.
Hi, Arash.
All right.
Can you go back? Hi, Arash.
Yes.
So here you mentioned the signing. I assume key generation, you also have a global abort, right?
The key generation is UC secure. It doesn't need any. I mean, it's already UC secure.
No, it's not UC. I'm just saying, so key generation and signing are both distributed, right? So in the distributed setting,
yes,
it's gonna be similarly as signing require abort, right? So abort in general is fine for two-party, maybe easy, but when you generalize to multi-party, let's say five-party, then would abort be a pain in practice?
So I just want to distinguish between two types of abort. One abort is harmless. You abort and you just need to restart the protocol. I mean,
Sure.
it's painful, but you need to do it. The other abort is that you abort and the other party learns something about your secret. So that global abort that I was talking about was the one that the party learns about the secret.
Yeah,
Now,
sure.
yeah. So but in general, the good abort, the non-harmful abort, yes, keygen may abort, any MPC protocol may abort. And our approach for handling aborts is that regardless of the number of parties, if an abort happens, we get rid of all our internal state and start the protocol from scratch.
I see. But why not? So have you ever implemented the broadcast channel at all? I mean, sometimes if you have broadcast channel, maybe you can get rid of this abort thing, right? Or
It
maybe
is possible, but it's not worth the effort. It's because the whole protocol runs in 70 milliseconds, right? Killing it and starting again isn't really that big of a deal.
I see. But so currently in your use cases, the number of parties is not that large. It's only a small number.
They are small, yeah.
Okay.
Yeah. They are not tens of thousands or even hundreds. They're a small number of
Okay.
parties.
Okay. Sure.
Yeah. All right. So, and the last piece is our technical rigor, our process. So everything we do starts with a theoretical justification. Actually, before that, I forgot to talk about it at the beginning of the talk. So our team is a product-driven team, meaning that the product team will come with a problem, either it's an efficiency or a new feature or whatever, and that's our starting point, as opposed to being a research-driven team where we just research for the sake of publication. Nothing against the researching for the case of publication, but our team is structured because we want to serve the needs of the Coinbase. So our starting point is a requirement that comes from product team, and then we either look and see if anyone else has already solved it, look on ePrint or other publication, and if they do, we make sure to read their proof and if needed, redo the proof, make sure that the use is secure and all of that. And if there is nothing out there, we do the research internally and then we publish the result in the appropriate time. So either way, we will end up with something we call a theoretical justification. This is not the actual paper itself. It is a document that describes why we think this protocol is good. It answers our need. What are the parameters that are important? So, for example, a paper may say use kappa, gamma, whatever, without actually giving them values. So we set those concrete parameters for the use case. If we deviate from the original paper, we also make sure to document that. So the theoretical justification is essentially a mixture of all of these to make sure that whoever has read the original theoretical paper can now understand what our mindset is, what parameter are we using, and then be ready to review the next phase, which is the specification. In the specification, we go into details and write it in a way that an engineer can read and implement. All right. So the specification is going to make a lot of implicit assumptions explicit. So, for example, in papers, you will see that that people would assume, yeah, of course, when you're sending a active curve point on the wire, the receiver need to make sure that it is on the proper curve in the proper subgroup. It's not infinity and all of that, right? So these quote-unquote trivial things on the theory side, we'll make sure to make them explicit on the specification side. And we have a lot of conventions to make it easy to read and follow, and I'll show examples of it in a few slides. So given the specification, you can then compare, given the theoretical justification and the specification, you can compare with the original paper and make sure that this specification is correct. All right. So now that we have the specification, we send it to our developers who will implement it, and then we will make sure that the developed code matches the specification. Okay, so that's the process that we do, and we have published all of that in our GitHub repository, and that's one of the things that you can use if you're looking for bugs. That's one of the places that you can do. You can read the original theoretical document, read the justification, see if we make any mistakes, or read both of those, read the spec and see if we made any mistakes, or read the spec and read the code and see if we made any mistakes. All right. Okay, so we also publish our design principles, secure usage, and how to deal with consent time, which I've already talked about, so I'm not going to go into details at this point. So to give you a taste of what each of those documents look like, let's start with our ZK proof document. So this is, I think it's almost 80 pages. It starts with a general treatment of the Sigma protocols, some batch equality check, the meta Sigma protocol. So instead of proving the security of each of the Sigma protocol for DH and DL and all of that, we just made one proof which considers all the linear combinations of that you would get. Right, and then LGML, PyE proofs, the PDL, which is the PyE discrete log proof, and unknown order discrete log proof. So we have quite a lot of and this is just one of the documents. We have theoretical justification for all of our protocols, and you can access all of them under the CB-MPC docs. All right, I'm not going into details here. But if you're interested in finding them, you can go to our README, find the protocol that you are interested, and you can both find the link to the theoretical document, read the link to the specification, and link to the code. And you can go ahead and do the comparison and find bugs. Hopefully you can find any, but if you do, let us know. I'll talk about that at the end. All right, so now let's see how does our spec and code look like. I'm not going to read through all of this. My goal here is to show you how easy it is to compare them. So on the left-hand side, you see the specification for EDDSA two-party signing, and on the right-hand side, you see the corresponding code. So for example, on line 40 of the code, you see that it's a loop, and we are just multiplying K1 with G. This is very simple. If you read cryptography papers or specs, you know what's happening here. It's a scalar multiplied by a generator, and you can see the corresponding code notation in the spec as well. K1.G gets you R1. So, or for example, in the code, using this job, which is essentially our networking abstraction layer, send from P1 to P2, all of this stuff, and you can easily match it to the spec, which is what's happening here. We have also tried to be both efficient and also accurate at the same time. So for example, here in the spec, we have that we should verify that R2 is a point on the curve, non-zero, and in the proper subgroup, right? But the corresponding code is missing. Instead, we have a comment here. And the comment is saying that that type of check is done inside the verification function. So instead of doing redundant work just for the sake of being the same as the spec, we make sure to comment these types of optimizations that we do. All right, so we are getting close to the end. Hopefully by now, I've managed to convince you to at least give us a try. And if you choose to do that, you can find us under GitHub and Coinbase/CB-MPC. It is MIT license, so there's no restriction on how you use it. We have a bug bounty program. The details of it is under our security doc, but essentially, there are two ways of reporting a bug. If you want to aim for the bug bounty, you can submit it through HackerOne. It has its own process. We'll discuss, and if the security, if the bug is valid, we pay out the corresponding bounty. Or you can choose to just email us directly, in which case you wouldn't be eligible for bug bounty, but we will work together, and then you can release responsibly or publish it however you choose to. So yeah, try to break us and let us know. That's it. Thanks for listening.